partial fractions is a method for rewriting rational functions in a form so that they can be integrated. A rational function is a fraction of polynomials, and we have one here, this x plus 11 divided by x squared plus 2x minus 3. Now, I see this, and I see the 2x, or the x squared plus 2x minus 3 is in the denominator, so it has been operated on in a way. There is a function that sends that to the denominator, which would lead me to believe that maybe substitution is in order. But if I take the derivative of x squared plus 2x minus 3, I end up with 2x plus 2, and the numerator, x plus 11, is not a constant multiple of 2x plus 2, so substitution doesn't work. However, the method of partial fractions will take this rational function with a quadratic denominator and rewrite it as the difference of two rational functions with a linear denominator instead. Each of those then can be integrated using substitution and logarithms. Okay? So I want to look at a couple of different instances of combining these rational functions and make some observations. I have 3 over x plus 6 minus 2 over x, 4x plus 1. The denominator, x plus 6, the highest power of x that we see is the first power. In the numerator, it's really kind of x to the 0th power. So the degree of the denominator is 1, the degree of the numerator is 0, the degree of the denominator is greater than the degree of the numerator. The same thing is true of the second term. The end result is a quadratic beneath a linear function. The degree of the denominator is 2, while the degree of the numerator is 1. The degree of the denominator is greater than the degree of the numerator. The same thing happens in the next two examples. Here I have a denominator of degree 2, degree 0 in the numerator, denominator of degree 1, degree 0 in the numerator. The numerator is quadratic. The numerator of the result is a quadratic. If you expand the denominator as cubic, 3 is greater than 2. In the last example, we have a quadratic denominator, a linear numerator, degree 2 versus degree 1, another one of these linear denominator constant numerator ones, and when we combine them, we again get a quadratic divided by a cubic. The upshot is that if we start off with any number of functions, rational functions, where the denominator's degree is greater than the numerator's degree, and add them or subtract them, we end up with a rational function of the same form. And it goes the other way. If we have a rational function of the form where the degree of the denominator is greater than the degree of the numerator, we can decompose them into things where we have quadratic denominators or linear denominators, and the numerators have degree less than the degree of the denominator. What if we have a rational function where the degree of the numerator is greater than or equal to the degree of the denominator? In that case, you would have to use long division in order to do that. I do not do that kind of an example in this video. I also only stick to rational functions where the denominator does not have repeated factors. So an x minus 4 squared will not be covered in this particular video. Let's look at our first example. I want to evaluate the integral of 3x dx over x squared minus 6x plus 5. The denominator, x squared minus 6x plus 5, has a derivative of 2x minus 6. 3x is not a constant multiple of 2x minus 6, so substitution is not in order here. Instead, we'll use partial fractions. The first step that you're going to do in partial fractions is you'll want to factor that denominator. So this factors as x minus 5 times x minus 1. Now my knowledge is that this will decompose into two fractions, denominator of x minus 5 and the denominator of x minus 1. The numerators will be a polynomial of degree less. Well, because the denominators are both linear, the numerators at best are constants. Here's how we're going to find those constants. We're going to break some mathematical rules in the process, but it's okay. I'm going to multiply both sides by the denominator of the left side. X minus 5, x minus 1, x minus 5 times x minus 1. I'm going to write out all the steps in this particular example, but after this, we'll save some time and only write sort of some of the crucial steps. We'll have x minus 5 times x minus 1. The left side, the x minus 5 is reduced to 1, as do the x minus 1s. We have 3x equals, and when we distribute, we'll have a over x minus 5 times x minus 5 times x minus 1 plus b over x minus 1 multiplied by x minus 5 times x minus 1. In the first term, x minus 5's reduce. In the second term, the x minus 1's will reduce. And we end up with the equation 3x equals a times x minus 1 plus b times x minus 5. We want to know what the values of a and b are. So here's how we're going to do it. This is where we're breaking some mathematical rules. I'll break them and then tell you how I broke them in just a moment. This is supposed to be a mathematical identity. Identities are supposed to be true for any value of x that we want. They should be true at 100, at 52, at pi over 6, whatever we want. In particular, it should be true when x is equal to 1. Why am I picking on 1? Because if I pick on 1, then x minus 1 becomes 0, and a is no longer a part of the equation. So let's try that. X equals 1. We have 3 times 1 equals a times 1 minus 1 plus b times 1 minus 5. 3 times 1 is 3. This first term is 0, and we get negative 4b. So b is negative 3/4. Let's try another value that will eliminate one of the variables. I have this factor of x minus 5. If x is equal to 5, we end up with 3 times 5 equals a times 5 minus 1 plus b, well, I actually know what b is, but I don't care right now, times 5 minus 5, that's going to be 0. We end up with 15 equals 4a, so a is 15/4. The real work in these problems is the algebra. So now we're going to take this integral, and I'm going to write it as the new integral. So it's a, which we just found was 15/4, divided by x minus 5, plus b, which we found was negative 3/4, divided by x minus 1. Oh, okay. Let's separate this as two separate integrals. We really don't need to do this, but I'm going to do it just for our purposes. 15/4 integral dx over x minus 5 minus 3/4 integral dx over x minus 1. So why did I do that? The reason I did that was because I recognized that the denominator here looks like 1 over x, almost. It's 1 over x minus 5. Now the great thing here is that the derivative of x minus 5 is 1, so even if you're not thinking clearly, you might stumble upon the correct answer. It's 15/4 multiplied by the natural log of the absolute value of x minus 5. Now what do I mean by stumbled upon the correct answer? When you take the derivative of the natural log of x minus 5, it will be 1 over x minus 5 multiplied by the derivative of x minus 5, which fortunately here is just 1. If it were like 2x minus 5, I would have to do something to compensate for that too, but I don't have to do that. If you're not comfortable with this, you're always welcome to use substitution, and you can let u be equal to x minus 5. For the second term, we end up with minus 3/4 times the natural log of the absolute value of x minus 1, and then we add our constant. Okay? So that's the general method when we have only linear factors in the denominator, and those linear factors are only to the first power each. For repeated linear factors, we would have to do something else which is not covered in this video. Now what I'm going to end up doing here is I'm going to end up skipping several steps here. Okay, so I'm going to end up skipping, well, I can write this out, the top line out, but I'm going to skip this step, and I'll probably skip this step, and we'll end up right at this step here. Okay, now I told you before that I was going to tell you where I broke a mathematical rule, and I haven't told you that yet. In the following step here, right at the x minus 1, I said let x be equal to 1. Doesn't seem like I did anything wrong. But where did this all come from? It all came from this expression up here. If I let x be equal to 1, I'm dividing by 0. Okay, it turns out that, yes, we're breaking a mathematical rule, but it works out just fine in the end, so we'll go ahead and do it anyhow. For our next example, we have a quadratic divided by a cubic. The degree of the numerator is less than the degree of the denominator, so we're okay to do what we want to do here. I'm going to first factor that denominator. So let's see here. I'm going to have 12, let's go back to black here, 12x squared plus 42x minus 5 divided by x. Okay, now I'm going to do a little bit of cheating here. We want to factor an x out of that denominator because it's in common with every term, which would leave me with 2x squared plus 3x minus 5. And I have to think about how to factor that. Well, it's certainly going to be 2x and x. And to get to 5, I either need to have 1 and 5 in that order or 5 and 1. And I think if we do 5 and 1, we're in good shape. We want a negative 5, but a positive 3. So I think I want to make a positive 5 there and a negative 1. And the inner term is 5x. The outer term is minus 2x. And we got what we wanted. Okay, so we end up with 2x plus 5 times x minus 1 in the denominator. Now, because I have 3 factors in the denominator, we haven't seen anything like this before, we're going to end up with 3 separate terms. So I'll have a divided by x, I'll have b divided by 2x plus 5, and I'll have c divided by x minus 1. Now we want to multiply by that denominator on the left side, the one that has the factor of x, 2x plus 5, and x minus 1. It gets a little bit messy here, but we end up with 12x squared plus 42x minus 5 equals, now let's think about what happens when you multiply by that denominator. A is divided by x, so the factor of x will cancel, but the other 2 factors remain. A times 2x plus 5 times x minus 1. And then b, when we multiply the second term by that denominator, the 2x plus 5 cancels, reduces, and we'll be left with an x and an x minus 1. And then the c over x minus 1, the factors of x minus 1 will reduce, and we end up with x times 2x plus 5. And now we can make some substitutions to get rid of factors. I see, first of all, that if I let x be equal to 0, we end up eliminating 2 of our terms. So we'd have 12 times 0 squared, which is just 0, 42 times 0, that's just 0, minus 5, equals a times 0 plus 5, which is just 5, 0 minus 1, which is negative 1. And I'm going to cut to the chase here. The b term and the c term both have a factor of x. Because they have a factor of x, and if x is 0, we're going to end up with b times 0, so I'm not even going to include those. Well, this turns out to be rather nice. I have negative 5 equals negative 5a, which means that a is 1. Okay? Ooh, I don't like that one. 2x plus 5, let's skip over that for a moment. X minus 1 I'm good with. If x is equal to 1, x minus 1 becomes 0. So 1 squared is 1 times 12. 42 times 1 is 42, minus 5. A has a factor of x minus 1 in it, so this factor of x minus 1, when x is equal to 1, will be 0, so the a term gets eliminated. If x is equal to 1, x minus 1 is 0, so we'll end up with a 0 there for the b, so the only thing that sticks around is the c term, so it's going to be c times x, we said x is equal to 1. 2x plus 5, if x is 1, we'll get 2 plus 5, which is 7. And let's see what equation we end up with here. We have 49 on the left side there equals 7c, arg, the 7 c's. And so c is going to be equal to 7. Okay, I've been putting this one off, but I'm not going to put it off anymore. If x is equal to negative 5 halves, what I'm doing here is I'm taking that 2x plus 5 and I've set it equal to 0. So x is negative 5 halves when I solve that. Okay, this is going to be fun. So I'm going to do this one a little more slowly. 12 times negative 5 halves squared would be 25 fourths. 42 will be multiplied by negative 5 halves, and then minus 5. Any term that has a 2x minus 5 in it will be eliminated because it will be equal to 0. So the very first term will be eliminated, as will the very last term. And so let's see here. So it's just the b term that sticks around. That's negative 5 halves. And then we have negative 5 halves minus 1. Okay, this is taking a little bit more work here. That's going to be 75 minus, 75 minus, that's going to be 21 times negative 5 is negative, so minus 105 minus 5 equals, that's negative 7 halves times negative 5 halves is 35 fourths, which is really 35 fourths times b. And so we end up with negative 35 on the left side equals 35 fourths b, which means that b is negative 4 if you do the solving there. So now it's time to put everything back into the equation here, or rewrite it as an integral. The hard part is actually done. So our integral is a divided by x. Okay, over here we have the a divided by x, and we found out that a is equal to 1, so we get 1 over x. Plus b is going to be divided by 2x plus 5. Well, we just figured out what b was. B is negative 4. And then c is divided by x minus 1. And I've lost track of what c is. C was 7, of course. So we get dx there. Now we can integrate each of these individually. Okay, 1 over x, I know the antiderivative of that. That's simply the natural log of the absolute value of x. I'm going to skip this middle guy for a moment. We dealt with something like 7 over x minus 1 in the previous slide. That's going to be 7 times the natural log of the absolute value of x minus 1. We'll put our plus c down there. Build a little barrier here. Okay, what about the guy in the middle? Well, we certainly have the minus 4. So let me do a little erasing here. Erase that. Put a minus there for the 4. I'm going to leave a little space. The natural log of the absolute value of 2x plus 5. I've lost, squeezed in there. Okay, why did I leave space? Because when you take the derivative of the natural log of 2x plus 5, it will be 1 divided by 2x plus 5, but you have to multiply by the derivative of 2x plus 5, which would be 2. Well, we haven't addressed that 2. To address the 2 that would pop out, we have to multiply by 1/2 to compensate for that. Again, if you take the derivative of the natural log of 2x plus 5, even with the absolute values in there, if you take the derivative of the natural log of 2x plus 5, you get 1 divided by 2x plus 5 multiplied by 2. So we have the 1/2 in there to eliminate the 2 that comes out from the chain rule. And so if we want to make this nice and pretty and a little bit larger to read, we get the natural log of the absolute value of x minus 2 natural log of the absolute value of 2x plus 5 plus 7 natural log of the absolute value of x minus 1, x minus 1 plus a constant. Still didn't have room for that constant. Bah. Okay, so we're going to do something a little bit different now. Each of the 2 examples we've done have had linear numerator or linear denominators in their, or linear factors for the denominators. This next one we have a linear factor and a quadratic factor. So this is going to be slightly different, and our end result is going to be slightly different as well. All right, so let's build a barrier there. So I know that 2x squared minus x plus 10 divided by x squared plus 1 times x plus 2 is going to be equal to, all right, I'm going to have one term which will have an x squared plus 1 in the denominator, a second term that will have an x plus 2 in the denominator. Here's where things change just a little bit. The denominator in the first one is irreducible. You cannot factor x squared plus 1, even if you introduce square roots and so forth. If you're relying on imaginary numbers, we certainly can do it, but we're not going to do that. Instead, x squared plus 1, I recognize as a quadratic. And remember the discussion at the beginning of the video when you have a quadratic denominator, the numerator could be anything up to a degree less than that degree. So degree less than degree 2 would be linear. So the numerator could be linear. And I like to think of linear functions as mx plus b, but I'll use ax plus b here instead. Let me emphasize that once more. The denominator has a quadratic, is quadratic, which is of degree 2. The numerator can be any polynomial of degree less than 2, which would include linears. Now, if a is 0, we end up with a constant. That's okay. But it could be up to a linear. The second factor, or the second term, has an x plus 2 in it. Its numerator can be any polynomial of degree less than a linear function. Well, a linear function has degree 1, so the best that could be is a c. That's the distinction between quadratic factors and linear factors. Quadratic factors will have linear numerators. Linear factors will have constant numerators. Now we're going to multiply both sides by the denominators. And we end up with 2x squared minus x plus 10 equals ax plus b. When you multiply by x squared plus 1 times x plus 2, the x squared plus 1s will reduce. And so we just end up with ax plus b multiplied by the other factor, the x minus x plus 2. C, on the other hand, will be multiplied by the factor that's not in its denominator. The factor that's in the denominator is x plus 2, so it will be multiplied by everything else, which is the x squared plus 1. All right, things deviate from what we've done before. So again, we can choose some x values that will allow us to eliminate some terms. In fact, the x plus 2, if I let x be equal to negative 2, I got some good things going on here. If x is negative 2, we'll end up with 2 times negative 2 squared, which is 4, minus negative 2 plus 10. The term that has the x plus 2 in it, when x is negative 2, that will be 0. 0 times ax plus b. And the very last term then, when x is negative 2, we'll end up with c times negative 2 squared is 4 plus 1. And I've made a mistake here. This should say equals in the middle. So let's make that say equals. On the left side, we have 8 plus 2, which is 10, plus another 10 is 20, equals 5c, which means that c is going to be equal to 4. Okay, because we have this quadratic, it's a troublesome one. We can't choose, okay, we can. You could choose x equals I to eliminate some stuff. Okay, we're not going to do that. That would eliminate the c, and we could do some other silly things. When I have only linear factors and a quadratic, a single quadratic, this method will work for us. Here's what I'm going to do. I'm going to go back to the equation that I have here. And I'm going to replace c by the value we just determined it was equal to. Okay, so I'm going to replace c by the 4 there. So I've got 2x squared minus x plus 10 equals the quantity ax plus b times x plus 2. And that's going to be plus 4 times x squared plus 1. Okay, so there is going to be some algebra magic happening here. 4 times x squared plus 1, we can distribute the 4 through there, so we get 2x squared minus x plus 10 equals ax plus b multiplied by x plus 2. That's plus 4x squared plus 4. Here we go. I'm going to subtract 4x squared and 4 from both sides. Again, I'm going to subtract 4x squared and 4 from both sides. If I do 2x squared minus 4x squared, I get negative 2x squared minus x. And I've subtracted the 4x squared. I need to subtract the 4. I have 10, but 10 minus 4 will be 6. Ax plus b times x plus 2. All right, so here's where the algebraic magic happens. This is supposed to be an identity. The right-hand side has factored, so the left-hand side should factor as well, and any known factors should be equal, which means that the left-hand side should have a factor of x plus 2. I don't know what the other factor is at the moment, but I will figure it out. Okay, so if it's x plus 2, when I FOIL it out, x times something should be negative 2x squared. Well, that's pretty easy to figure out what that's going to be. X times negative 2x will give me the negative 2x squared. And then 2 times something should be 6. 2 times 3 is 6. And so we'll have negative 2x plus 3. If you multiply it out, it works out perfectly. 2 times negative 2x will give me negative 4x. X times 3 gives me positive 3x. Negative 4x plus 3x gives me the negative x in the middle. And when we divide both sides by x plus 2, we find out that ax plus b is exactly negative 2x plus 3. Okay, so now we're going to split this up. This is going to be equal to the integral. I'm going to put my linear one first because it's not so obnoxious. C was equal to 4, so we've got 4 over x plus 2. And then I have plus, we said ax plus b was negative 2x plus 3 over x squared plus 1 dx. Okay, so the first one is nice to evaluate. It's like we've seen before. It's going to be 4 times the natural log of the absolute value of x plus 2. It's the second one that's going to give us some fits. Let's look at it really quickly. I see an x squared plus 1 in the denominator, which leads me to believe maybe I should take the derivative of the denominator. Well, that would be 2x. Hey, look, in the numerator I have a 2x, but darn it, I have a plus 3 there. So if the plus 3 weren't there, I would be able to use substitution. Now, x squared plus 1 reminds me of a function whose function's derivative. In fact, 1 over x squared plus 1 is the derivative of the inverse tangent. So if I had 1 over x squared plus 1, or even 3 over x squared plus 1, I'd be able to use the inverse tangent. So if the minus 2x weren't there, and I had 3 over x squared plus 1, I'd be able to do it. I said if I eliminated the 3, I could do it with the negative 2x up there. If I eliminated the negative 2x up there, I could do it with the 3. So let's make this 2 separate integrals. Let's make it negative 2x dx divided by x squared plus 1 plus the integral of 3 dx divided by x squared plus 1. Okay. If you remember, the first one I said, hey, we're going to do a substitution, and I know I'm running out of room here, so I'm going to do something in blue up here. I'm going to let u be equal to x squared plus 1 for this particular term. Then du is 2x dx. Okay, well, the negative that's here, I can just pull out into the numerator. So 2x dx is exactly what du is, and let's go ahead and finish this off. So we have 4 times the natural log of the absolute value of x plus 2. I said we were going to pull the negative out. This one I'm using substitution on. The negative we've pulled out, 2x dx is du. X squared plus 1 is just u. And now it looks familiar. That's going to be a logarithm. And then this last one, we argued that if it were 1 over x squared plus 1, I would use the inverse tangent. We can move the 3 out in front of the integral. 1 over x squared plus 1, this is going to be the inverse tangent of x plus a constant. Okay, so we're almost done. Natural log absolute value of x plus 2. When I take the antiderivative of 1 over u, I get the natural log of the absolute value of u. I wrote x, u, plus 3 times the inverse tangent of x plus c, and I'm going to make one last substitution and I'll be done. I'll have 4 times the natural log of the absolute value of x plus 2 minus the natural log, and I'm going to make one observation here. U was equal to x squared plus 1. If you square a number, the smallest result you can get is 0. If you take 0 plus 1, you'll get something that's 1 or larger, always a positive number. So I don't really need those absolute values there. Natural log of the absolute value of x squared plus 1 and then plus 3 times the inverse tangent of x plus a constant. One more. All right. For this last example, we once again have an integral where the degree of the denominator is greater than the degree of the numerator, so it's a good candidate for integration by partial fractions. And also the derivative of the denominator is not equal to a constant multiple of the numerator. We'll factor the denominator first. Observe that there is an x that can be pulled out of there. So we'll have x times x squared plus 4. Now that x squared plus 4 reminds me of x squared plus 1. 1 over x squared plus 1 is the derivative of the inverse tangent, and so it's going to be related to that. We'll provide the formula for the generic sort of x squared plus a squared antiderivative when you have that in the denominator. But we have two factors there. One is an x, one is the x squared plus 4. X is of degree 1, so we could have only a constant in the numerator. But x squared plus 4 is a quadratic, so we can have up to anything degree 1 or lower, so bx plus c will go up there. If we multiply both sides by the denominator, we have 6x squared minus x plus 20. And then when you multiply x times x squared plus 4, the x will cancel, so we end up with a times the quantity x squared plus 4 plus bx plus c. When you multiply that, we end up with just x. Once again, we're going to choose values of x that will eliminate lots of terms at once. And if I choose x equals 0, I'm good to go. So on the left side, it's going to be pretty clear that we'll just end up with 20. On the right side, we'll have a times 0 squared plus 4, so a times 4. This last term here will just be 0, which means that a is equal to 5. As we did in the previous example, we'll take that a equals 5 and substitute it into this equation. We'll have 6x squared minus x plus 20. It's a big plus there, equals 5 times x squared plus 4 plus the quantity bx plus c times x. Now we distribute the 5 through. 6x squared minus x plus 20 equals 5x squared plus 4, not 4 anymore, now 20. And then plus, we'll just leave that x factored out. We'll see why that's important to do or not do, as in not distribute. If we subtract 5x squared from both sides, we end up with x squared. We have minus x. There's no x on the right side to simplify with that one, but we do have a plus 20 on the left, a plus 20 on the right. When we subtract, we'll get 0. And this is equal to bx plus c times x. Both sides are polynomials. Polynomials, if you have two equal polynomials, they will factor the same way. So since the right side has a factor of x, the left side should also. We'll have x times x minus 1 equals bx plus c multiplied by x. So that means then that this x and this x, if we divide both sides by x, those will reduce, and we end up simply with x minus 1 equals bx plus c. Okay, so x minus 1 is equal to bx plus c, and we can replace our integral now by the integral of a over x. A is 5. And then bx plus c is going to be x minus 1 over x squared plus 4 dx. Okay. So, as before, whenever we have these quadratics, if you end up with two terms in the numerator, you're going to need to separate those two terms into two separate integrals. The 5 over x is going to be 5 times the natural log of the absolute value of x, plus the integral of x dx over x squared plus 4, plus, well, let's make that a minus 1, so just dx over x squared plus 1. X squared plus 4, I'm sorry. Okay, so the formula that we need to know in the next, most of the time, the next thing that students learn are formulas doing integration by tables. And so one of the formulas for integration that we have is this integral of du over u squared plus a squared is 1 over a times the inverse tangent of u over a. So we'll use that for this very last one. Now we have to think about, hey, wait, u squared plus a squared, so x squared plus what squared would be 4, so we'd have to do this with a equal to 2. Now for the one in the middle, just like we did with the previous example, we're going to use substitution for that one. So what we'll do is we will say over here, I'll do it down towards the bottom. Let's do this in red so you can know where it's coming from. U, I'm going to let be equal to the x squared plus 4 that's in the denominator. Du is 2x squared, or 2x dx. We're missing the factor of 2, so we'll have 1/2 du equals x dx. All right, so we're ready to make the substitution. The substitution is for this middle guy here. So this is going to be equal to 5 times the natural log of the absolute value of x. And then when we make our substitution here, we're going to remember we have this 1/2 that's out front. So 1/2 times the integral, x dx was 1/2 du, and the denominator is u, minus, and now we get to use our new little formula over here. A is equal to 2, so it's going to be 1/2 times the inverse tangent of u over a, well, our u is x over 2 plus a constant. And we're almost done. We've got 5 times the natural log of the absolute value of x plus 1/2. The antiderivative of du over u is the natural log of the absolute value of u minus 1/2 times the inverse tangent of x over 2 plus c. And we make our final substitution here. Because u is x squared plus 4, and x squared plus 4 is always greater than or equal to 0, just like in the last example, we can just make this the natural log of x squared plus 4, and then minus 1/2 times the inverse tangent of x over 2 plus c.